In this video, I want to talk about ways to use the matrix representation of an equation to solve that equation, that system of equations, fairly quickly. So we're going to look at systems of linear equations, put them into a matrix representation, which is what we talked about in the last video, and then we're going to talk about what do we do to this matrix to solve the system of equations. And to do that, I'm first going to talk about just the matrix itself, just operations that we can perform on the matrix. And so last time we talked about all of the row operations that we could do. Those included the replacement, where we replaced one row by the sum of itself and a multiple of another row. The interchange operation, where we could just flip or interchange two rows, and the scaling operation, where we could just multiply all entries in a row by a non-zero constant. Those are going to be the operations we're allowed, but I want to think about what do we want what are we trying to do to the matrix? So to do that, we are going to define a couple of things. The first one that we're going to define is what we call echelon form, or this is sometimes also called row echelon form. So when we have a matrix, we want to get that matrix into row echelon form. So we need to know how that is defined. So the first thing that has to be true for a matrix to be in row echelon form is that all non-zero rows, and what I mean by a non-zero row is any row that has any number other than a zero in it. So a zero row would be a row that is just completely zeros. A non-zero row would be a row that has some non-zero number somewhere in that row. So all non-zero rows are above any rows with all zeros, or any zero rows. And the second thing is that each leading entry, and what we mean by a leading entry is the first non-zero number in a row. So each leading entry, the first non-zero number in a row. So each leading entry in a row is in a column to the right of the leading entry of the row above it. So just quickly, what does this look like? Well, if you've got zeros, if you've got any rows that are all zeros, those are at the bottom. So any rows with all zeros just sit at the bottom. Any rows that don't have zeros sit above it. So maybe there's something like this. And since we've got this, the second rule says that the leading entry of any row below that row has to have its first leading entry somewhere to the right. So that would be in echelon form, because as I move downward, my leading entries move to the right. And then the rows that don't have leading entries, the all zero rows, are at the bottom. So I'm not going to worry a huge amount about putting that in right at this point, but there is a lot of textbooks add a third rule, and that is that all entries in a column below a leading entry are zeros. This, you don't have to have this rule because this rule is automatic. If you meet 1 and 2, then the third rule is automatically met. So if you're including this rule, it's just because you're wanting to emphasize the fact that once you find a leading entry to a row, everything below that is 0. And that will be something that is important for us, a way to think about it, but it is automatic from the first and second rule together. So this is what echelon or row echelon form is. And so if we think about the shape of an echelon form matrix, it looks something like this. Maybe you've got some kind of a leading non-zero, a leading entry in a row, and then whatever numbers. It could be anything moving out to the right from there. Because that's the leading entry, everything below it has to be zeros. And then there isn't necessarily, maybe this is a 0, maybe it's not. I don't know how many times this goes. But eventually we get to another leading entry. And to the right of that could be anything at all. But because it's a leading entry, everything below it has to be zeros. And maybe there's a leading entry directly below that. To the right of that could be anything at all. But because it's a leading entry, everything below it has to be zeros. Maybe the next one looks something like this. And everything below it has to be zeros. And maybe the last row is just all zeros. I don't know. It could look a little bit different. But the important thing to notice is if we look at this, we follow a stair-step pattern. So what do I mean by that? There is a stair-step pattern based on where the leading entries are that you can look at. And it always moves to where the first non-zero entry in every row follows this stair step walking down the stairs pattern. And so that's the big idea about what echelon form looks like, is getting it to where there's kind of this lower left-hand corner is all zeros, the upper right-hand corner could be whatever it is, and there's this stair-step pattern down the middle for your leading entries. Echelon form is very useful, but we can do better. We can do it what we call the reduced echelon form. This is also called the reduced row echelon form. And both of these terms are just fine. You can use either one interchangeably. They mean the same thing. But we're going to, so I will go back and forth between them, because when I learned this, I always called it the reduced row echelon form. If you have a calculator that can calculate this, it will probably be referred to as RREF, which stands for reduced row echelon form. But this is the form that is going to be most useful for us, is if we can take this, and it's a reduced row echelon form, so it is an echelon form or a row echelon form, but it adds 2 more rules. Rule number 4 then would be that all leading entries are 1s. And rule number 5 says each leading entry is the only non-zero entry in its column. So what do we mean by that? Well, I'm just going to copy the row echelon form that we used earlier, and I'm going to update it to look like a reduced row echelon form. So the first thing I'm going to do is I'm going to get rid of the stair-step pattern, not because it disappears, but because that's not what I'm emphasizing. The leading entries now have to be 1s. So I've reduced all the leading entries from whatever numbers they were down to 1s. And everywhere where there is a leading entry, it's not just the numbers below it that are zeros, it's also the numbers above it. So this is what our reduced row echelon form or our reduced echelon form of a matrix looks like. We've got 1s as leading entries in every row, and if you've got a leading entry, it is the only non-zero entry in that column, and we still have that stair step downward. That just looks like that. So the reduced row echelon form is going to be very useful for us because it's going to make it very easy for us to read solutions. If we can get a matrix that represents a system of linear equations into reduced row echelon form, then our solutions that's the easiest way to get our solutions. So it becomes important that we get to where we can actually do these calculations. The reason it becomes super important, though, is because of a theorem that we have. And so the theorem we have is, sorry about that. The theorem we have says that each matrix is row equivalent so that if you remember from the first lesson, row equivalent means that you can get from one matrix to the next to this matrix by using just those row operations. So each matrix is row equivalent to exactly one reduced row echelon form matrix. And if a matrix was row equivalent from the first lesson that we did, from the last video, we learned that if a matrix is row equivalent to another matrix, then it represents the same system of equations. It has the same solutions. The system of equations that is represented by this row has the same solutions as the other matrix. So these two matrices, if you can get from one to another, if their two matrices are row equivalent, they represent the same system of linear equations. And so this means that if we can get a matrix into a reduced row echelon form, we have all the information about that system of linear equations. And since we have this, so since each matrix, let's call it A, has a unique reduced row echelon form we can locate the position of every leading entry, or leading one, in the reduced row echelon form of that matrix A. So we can figure out what locations those leading entries are, those leading ones are, in the reduced row echelon form. And we can call those, so we call these locations pivot positions. And every column, so each column that contains a pivot position is called a pivot column. So if a column has a pivot position, that's called a pivot column. So let's do an example. Let's find some pivots for a matrix. So let's consider the equation, the system of equations that says x3 minus 2x4 is equal to 0. x1 plus 2x2 plus x3 minus 3x4 minus x5 is equal to 4. 2x1 plus 4x2 plus 2x3 minus 6x4 plus 3x5 is equal to 13. And x1 plus 2x2 minus x4 plus x5 is equal to 4. If I want to write the augmented matrix that represents this system of equations, that would be the augmented matrix 0, 0, 1, negative 2, 0, and I want this to be a 2 instead of a 0. So 2. And then 1, 2, 1, negative 3, negative 1, 4. 2, 4, 2, negative 6, 3, 13, and 1, 2, 0, negative 1, 1, 4. This is that augmented matrix. So I want to look at this matrix, and I want to find its pivots, and I'm going to do that by getting it into row echelon form. I'm actually going to, for me personally, I usually go a step further than just getting it into row echelon form. I usually go ahead and take it all the way to reduced row echelon form, because that's the form that is most useful for us. So we're going to take this and we're going to go through the process of getting this into reduced row echelon form so that we can find all of the pivots and see what we get from that information. So I'm going to copy this so that I can go to a new page, and we're going to work with that matrix. So the first thing that we do, we start from the left column. And we check to see if that column is all zeros. So since the left column is not all zeros, that means that it is a pivot column. So that first column is going to be a pivot column. Now, what I want is the top row to have a leading entry in that column. Unfortunately, in this case, the leading entry for the top row is in the third column, not the first column. So I'm going to have to swap or interchange two rows. And it doesn't matter which two rows I interchange, but I'm just going to choose to interchange row 1 and row 2. That will get me a non-zero starting point. So to do that, I'm going to have now 1, 2, 1, -3, -1, 4, and 0, 0, 1, -2, 0, 2. And then the other two stay the same. 2, 4, 2, -6, 3, 13, 1, 2, 0, -1, 1, 4. Now we have a pivot already located, and that pivot actually already happens to be a 1. So this isn't required for getting it into row echelon form, but if we want to go all the way to reduced row echelon form, we would eventually need to turn that into a 1. In this case, it already is a 1, which makes our life easier. Now, the next step is I need everything below that to be all zeros. I'm going to do this by adding -2 times row 1 to row 3, and then -1 times row 1 to row 4. So the way I like to write that is row 3 is going to become, so I draw an arrow to row 3 because this is what it's going to become. It's going to become what it currently is, row 3, plus -2 times row 1. And I'm going to do the same thing, and I could do this in 2 steps, but I'm just going to go ahead and do this addition for both of the additions at the same time. So row 4 is going to become what it currently is, row 4, plus a -1 times row 1. So when I do this, my first row and second row stay the same. And now I add row 3 and -2 times row 1. So the first space is 2 plus a -2 times 1, so 2 times plus -2 is 0. The next is 4 plus a -2 times row 1, so 4 plus a -2 times 2 is 4 plus -4 is 0. The next one is 2 plus -2 times 1, or 2 minus 2 is 0. The next is -6 plus -2 times -3, which is -6 plus 6 is 0. The next one becomes 3 plus -2 times -1 is 3 plus 2 is 5. The next is 13 plus -2 times 8, plus -2 times 4 is 13 plus a -8 is 5. And for the fourth row, I'm taking row 4 plus -1 times row 1, so that becomes 1 plus a -1 is 0, 2 plus a -2 is 0, 0 plus a -1 is -1, -1 plus -3 times -1 is -1 plus 3 is 2. And then 1 plus -1 times -1 is 1 plus 1 is 2. And 4 plus a -4 times, 4 plus 4 times a -1 is 4 minus 4 is 0. Now, I've zeroed out everything below that first pivot, so I don't need to worry about anything to the right of that pivot in that first row. So I'm going to look at the submatrix that ignores the rest of that column and the rest of that row. So I'm just looking at this submatrix that is down and to the right from that pivot. And I repeat the process on that submatrix. So we start from the left column of the submatrix. And the first column, or the leftmost column, is all zeros. And if you look, you can see that that's not true because there is a 2 there. But remember, we're looking in the submatrix. So we don't care about anything above in the first row. We only care about things below and to the right of the lines that I drew in. So below and to the right means that I'm looking at these sections for my column, and those sections are all zeros. So I just move on. So what I'm going to do is so we move to the right. And that means now we're looking at the submatrix made by moving over to the right by 1. And we look at the leftmost column. And looking at that left column, I have a non-zero entry in the submatrix, so this is going to be my next pivot position. And it turns out I've already got at the top a 1. That is going to be my pivot position. So in this pivot column, I have this pivot position that already has a 1. That worked out nicely because it means that I'm already getting closer to reduced row echelon form. So now I need to zero out everything below that 1. To do that, I'm going to take and store in row 4, replace row 4 with what it currently is, row 4 plus row 2. When I do that, I get 1, 2, 1, -3, -1, 4. The first row doesn't change. 0, 0, 1, -2, 0, 2. The second row doesn't change. 0, 0, 0, 0, 5, 5. The third row doesn't change. But the fourth row becomes 0, 0. -1 plus 1 is 0. 2 plus -2 is 0. 2 plus 0 is 0. 0 plus 2 is 2. And I'm now working in this submatrix. Let me write that correctly, because 2 plus 0 is 2, not 0. But I'm now in this smaller submatrix. Inside this submatrix, the first column is all zeros. So I'm going to move to the right and work in this submatrix. The first column is now the first column in this submatrix now has a non-zero entry, so this is going to be a pivot column. And I want to zero out everything below it. Now, there's a couple ways I can do that. One is I could just immediately say, well, let's take R4 and replace it with itself plus a -5/2 of, a negative 2/5 of R3. And if I do that, I'm going to zero out that column. But that's a little bit harder to see. So what I prefer to do is, instead of doing that, I'm just going to scale this pivot to 1, because I'm going to eventually want to do that anyway to get to reduced row echelon form instead of just row echelon form. In that reduction process, I'm going to want to get there anyway. So I'm going to just scale that first. And so I'm going to replace R3 with 1/5 of R3. Doing that is going to give me the matrix. Well, the first row is unchanged. The second is unchanged. The third becomes, well, 5 times 1/5 is 1, and 5 times 1/5 is 1. Now I need to zero out everything below that leading 1. So to do that, I'm going to replace row 4 with row 4 plus negative 1 times row 3. When I do that, I get the first row remains unchanged. The second remains unchanged. The third remains unchanged. And the fourth becomes, I'm sorry, that I should be replacing it with negative 2, not negative 1. Negative 2 times R3. The last row becomes 2 plus a negative 2 is 0, and 2 plus a negative 2 is 0. And now I would be working in this submatrix. But that submatrix is just all zeros, so I'm done. So I can just stop at this point. And that is a matrix in row echelon form. In fact, I'm slightly more than row echelon form because I've already turned all the leading entries into 1s. Let's go ahead and take it one more step. Actually, before I do that though, let's locate our pivots. So in the row echelon form, I look at where my leading entries are. Those are my pivots. So in my original matrix, I have the same pivots. Now, are they real useful for us in that original matrix? Not really, but those are the pivot positions. So they don't change as you go through the row echelon form. Where the pivot positions are doesn't change, and the pivot columns do not change. So let's go ahead and take this and we are going to copy this to the next page. And let's go ahead and get this down to reduced row echelon form. And to turn this into reduced row echelon form, I need to zero out all of the values above my pivots. So my first pivot in this space already there's nothing above it, so it's already done. So then I look at my next pivot, which is this one. That one, I need to zero out all the rows above it. So, sorry about that. So to do that, I'm going to take and replace row 1 with row 1 plus a negative 1 times row 2. And that gives me 1, 2. 1 plus a negative 1 is a 0. Negative 3 plus negative 2 times negative 1. Negative 2 times negative 1 is 2, so negative 3 plus 2 is a negative 1. Negative 1 plus 0 is still just 0. And then 4 plus a negative 2 is 2. The second row stays the same. The third row stays the same. And the fourth row remains the all zeros. Now my column 3, the pivot column 3, is now all zeros except for the leading entry. I have to figure out how to reduce this pivot column 5. And to do that, I need to remove all the non-zero entries above it, which means I need to replace row 1 with row 1 plus row 3, which gives me 1, 2, 0, negative 1. Then I get negative 1 plus 1 is 0, and 2 plus 1 is 3. Then the next row is 0, 0, 1, negative 2, 0, 2. The next row is 0, 0, 0, 0, 1, 1, and then all zeros. And this is now my reduced row echelon form matrix. And if you notice, it has that stair-step pattern in it. And so this is our reduced row echelon form matrix. And so why is this a good thing? Why is this valuable for us? Well, once we've got it into this form, remember each column represents a different variable, and the last column is that augmented column. It's what these things add up to. So I have a equivalent system of equations that looks like x1 plus 2x2 minus x4 is equal to 3. x3 minus 2x4 is equal to 2. x5 is equal to 1. And then the last row doesn't represent anything. It just says 0 is equal to 0, which is true no matter what my x values are. So now I can look at this system of equations and I have a little bit more information. I know exactly how to write these down. So if I wanted my solutions, I could write my solutions to this system of equations are, well, from this first equation, I can find out exactly what x1 is equal to. x1 is going to be equal to the 3. I'm just solving for x1, so it's going to be 3 minus 2x2 plus x4. x2, I don't have any equation where x2 corresponded to a pivot. So x2, we just say is free. x3, from this second equation, I get that x3 is equal to 2 plus 2x4, where I just solved that for x3. x4, once again, I don't have any piece that corresponds to this x4 as a pivot. x4 is not in a pivot column, so x4 is free. And then x5 is equal to 1. And so this is my solutions. Now, because I have free variables, x2 and x4, we have infinitely many solutions. So to figure out if a point is, to figure out any particular solution, I have to pick an x2 and an x4. So for instance, if I said, let's let x2 equal 0 and x4 equal 3, once I know those two pieces of information, I have a specific solution. So then I would have the solution x1 is equal to 3 minus 2 times 0 plus 3, which is equal to 6. x2, because I set it there, is equal to 0. x3 is equal to 2 plus 2 times 3, which is equal to 2 plus 6 is 8. x4, I set it equal to 3, so it's equal to 3, and x5 is just equal to 1. And so for picking x2 equals 0 and x4 equals 3, I get this solution set. But I could also do any other two numbers. I could do, let's say, x2 equal -1 and x4 equal, I don't know, 1. Then I get that x1 is equal to 3 minus 2 times x2. So 3 minus 2 times -2 is 3 plus 2 plus x4 is plus 1. So 3 plus 2 plus 1 is 6. x2 is equal to -1. x3 is equal to 2 plus 2 times x4, or 2 plus 2 times 1, or 4. x4 is equal to 1, and x5 is equal to 1. There's another solution. And no matter what two numbers I plug into x2 and x4, what we call the free variables, I get another solution. And so what this does is it allows me to say, once I know where the pivots are, those pivot columns correspond to the x's that are the basic variables, or sometimes called the fixed variables, and the columns that are not pivot columns are free variables. And any free variable is, you can just set them to whatever you want to get another solution. Okay, so I think that is where we are going to stop for this video. We've got the process of getting it into reduced row echelon form. Once you're in reduced row echelon form, you can use those solutions to get to figure out exactly what your answers are. Now, there is one more thing I want to show you, and that is, actually, let's do two things. The first is, suppose you have a matrix and you go through the process of getting it into reduced row echelon form, and it looks like this. Well, now this is representing x1, x2, x3, and what they're equal to. Right now, I can read my solutions as x1 is equal to 1, x2 is equal to 3, x3 is equal to 5. There's exactly one solution because there are no free variables. So if this is what your matrix looks like, then you get exactly one solution. If your reduced row echelon form matrix looks like this, though, where I've got a leading entry in that final column, then let's think about what that last row says. That last row says 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 1, which is 0 is equal to 1. That's not true. That cannot ever be true. So this, the system of equations that led to this reduced row echelon form matrix, has no solution. Okay. Now we're actually going to stop, and I will talk to you guys next time.